So I'm going to introduce the final speaker of the seminar, and this is Dr. Andries Botha. And Dr. Andries is trained as a chemical engineer at the University of Pretoria. He has an MBA and a PhD from the University of Pretoria and a master's in the management of technology from the Massachusetts of Technology. He started his career at the Council for Scientific and Industrial Research with a focus on water and effluent management. He was introduced to systems thinking and systems dynamics in the early 1990s and found a calling as a systems dynamics modeler. In 1994, he founded Dynamic Strategies, a company focused on solving complex problems using systems dynamics. In 2007, the whole team joined Toyota South Africa. Andries headed the team that designed, constructed, and set up the new Toyota parts warehouse in Boksburg. In 2020, he headed up the construction project for phase 2 of the parts warehouse. Andries is a founding member of the South African chapter of Systems Dynamics Society and the 2020 president. He's also our current chapter president. Andries is also a visiting lecturer at the Department of Mechanical, Industrial, and Aeronautical Engineering at the University of Witwatersrand. He volunteers as an educational counselor at MIT and interviews applicants from South Africa and various countries in Africa. He is a keen bridge player and avid mechano collector. Andries is supported by a hugely patient wife, Roxanne, and daughters Rolandi and Cherise. Over to you, Dr. Andries.
Sorry, before we get into that, can I ask Jean-Jacques to please switch off his camera? I'm not sure if I'm saying your name correctly, sir. Jean-Jacques. Jean. I'm not good with French.
Good evening, everybody. So thank you for that introduction, Phyllis, and Nalini, thanks for that detailed explanation of a very simple model. I'm going to try and wow everybody and beat that tonight, so I hope you've got your big boy pants on for the modeling section. So not really true. So what I want to do today is to just try and get it to the real deal, because I think sometimes we as practitioners tend to make life easy when we come to modeling because we've done this before. It's not the first time. What I want to try and do today is to try and make it practical and simple for everybody to understand. At any point, if you've got questions, I can't see you raising your hand or anything, so please ask Nalini or Phyllis or Young to stop me and ask the question, because I think it's important that we share that knowledge. And just not to be outdone, I put my full list of company affiliations at the moment. I'm pretty busy, but system dynamics is so much fun for me that, you know, any opportunity I get to do it, I'll find a spot and I'll start getting involved with that. So basically what I want to do is to say, well, you know, I've got the software. I am one of those RTFM. I hope everybody understands the abbreviation RTFM. As engineers, we tend to do that way too late in the project. So I'm going to ask the question, I want to build a model. What do I do? Then I'm going to go to and say, but does this model make sense? Because it's easy to build, but does it make sense? And then once I have something that works, what do I do now? And then finally, I also want to run us through a number of function tests where I want to demonstrate how, you know, sometimes I want to do something peculiar with a system dynamics model, and I don't always know whether the functions that's built into the system will do what I want it to do. And I've just developed a little tool which I can use to then analyze and understand that. What I'm going to do is basically do everything from scratch. So let me start off with the process. I think Nalini has explained a very good methodology to follow. And I think for me, the most critical part of the domain that you're trying to model or the problem you're trying to model is to fully understand it. So you need to understand the domain, you need to understand the scope of your model, but as importantly, you have to understand the purpose of the model, because the reality is that, you know, you all saw that iceberg model. those perceptions we create also means that we ask different questions of a model. And by understanding what the questions are that we're asking, that also guides how we put the model together. And then there's a few decisions we have to make. Once we start with a model, we've got to make decisions as to what are stocks, what are flows. Nalini has already spoken about the time domain. Do I model it in weeks, in days, in months, in years, in seconds, in minutes? How long do I make that time domain? Is it 1 year, 10 years, 200 years? What is the correct number to use for the specific purpose that the model is for? And then I decide also what is the level of complexity that's sufficient. You've seen the model Nalini has put on the table, extremely detailed. But that's the level of complexity that they need to answer the question at. That's the level of detail where we need to ask the question if we're trying to plan a national network. If I, for example, let's take my case study. For example, if I want to look at populations, populations are very simple, and I've got two options. I'm going to just try two options. The one is I'm going to look at the global population. And basically the population consists of us, the people. The only way to get into this population is through a birth. And the number of births that we have per year is a function of the birth rate and the population. And the only way to go out of this population is to die. As I always say, astronauts don't count. So we're going to ignore the people who go off in space and come back. We'll just assume they're part of the general population. And then what you'll see is, in terms of deaths, I don't like the idea of a death rate. It's a very scary word to me. I'd rather look at life expectancy, because then I can input my plan of a 200-year life expectancy and all the plans I've got for that. So first thing I want us to do is to say, and I'm going to jump between the two bits and pieces here, so you'll have to be patient with me on this every time. Let me go to, and what you'll see is I've got a weird version of Stella. I don't know, I think version of Stella. It's one that is in existence. I think they do it because I ask very nicely. I don't like Stella. I'm a, I think, supporter. Please shout if anything is too small for you to read, then I can change. I'm just working on a peculiar screen here. So the first thing that I've done is, for those who haven't done system dynamics before or used the Stella environment, on the left-hand top, we've got basically 4 modeling tools. We've got a stock, we've got a flow set, we've got converters, and we've got connectors. So I've already placed my first stock down there, and now comes my first decision. So what is the stock going to be? And I think I mentioned it already. We're looking at a population of people. So I'm going to call it people. One of the annoying things they've done is they've added a spell check. So they correct you if you make any mistakes in your spelling. You can't get away with it anymore. So I've got my population of people. I've got my births, which is a flow. And I have my deaths, which is a flow that flows out of the population. Let me just do that. So very important factor that you'll see is I've basically linked this flow, which starts from an infinite sum, so I can have as many births as I want to. There's no limitation on that. I've got my births, which will be controlled by some sort of a function, and that then ends up in my population stock. Very important little trick I can teach you is if you move the population like that, your stock like that, and the flows come with, it means the connection exists. Sometimes you think you've made the connection and sometimes you've missed it. That's a little quick test that I always do to just confirm that I've done all the connections that's necessary. On the outflow side, we've got the deaths, and again, you'll see here's a cloud. So basically, this is an infinite sum. So we've got enough space to bury whomever passes away. I'm now going to place my 2 converters. The first one, which is my birth rate. And I'm going to place the second one, which is my life expectancy. And now I need to make connections. So the population we know influences the births, and the birth rate also influences the births. So I've got my first loop basically built up. If I go to the death side, I know that the population affects the number of people that can pass away, and the life expectancy affects that. And there's our model. So simple enough. We can now start asking the next question. Okay, so next question we have to ask is, how do we make this thing run? Does my model make sense? So I can put in simple equations there, or I can put in complex equations. I can take a complex environment and I can change it into a structure and end up with a much more complex systemic structure underneath that will then give me a specific type of behavior that will replicate that I might have had to aggregate into a complex function if I was going that direction. And then there's also this process of validation, calibration. How do we make sure that this model makes sense? So as you can see, I did this last night. I got the same answer, so we're all in good company here. So, but before I proceed, let me show you how we make this model of mine run. And again, very important, we have to ask a question, and that is, what time unit are we going to run this model in, and for how long do we plan to run the model? So let me go here to my run specifications. And the reality is we want to, of course, run this in years. So that's a simple one. And I want to start, let's start in 2022, sorry, 2020. Actually, let's start in the year 2000. Sorry, my data is 2020. So let's start in 2020. Any thoughts, and you can put your numbers into the chat, and Nalini or Phyllis can read it to me. What time frame do you think makes sense in terms of how long I want to simulate if I want to look at a population? I can pick any number. So I can start and I can say, well, what about 200 years? Any takers for 200 years? Nalini, are there any people putting numbers up?
No.
No.
No number yet. Guys, do you want to put it in the chat? Okay, Bandile says 200 is good to go. Sunita says 100. Ruandre says 150.
Okay, so let's think through this. At the moment, the global life expectancy is 72 years. So if I put in 200 years there, I've basically only got 3 generations. And if we really want to know about the globe, do we really plan only for 300 years, or do we plan, or for 200 years, or should we plan for longer? And that's the kind of question you've got to really ask yourself in terms of what you want to understand from the model. So for example, let's say we want to know if the world can sustain the current life expectancy and the current birth rate without collapsing. Let's take a 200-year window. What to me is really annoying is when people do populations and they go and build a complex model and then run it for 10 years, because 10 years, it's insignificant in terms of human population. If you were looking at a deer population where the life expectancy is 3 years, that's a reasonable number. So very carefully think before you start putting down exactly how long you want the simulation to run. Okay, so let's make this model run, and I'm going to do it in a peculiar fashion so that you can see, first things first, is that we can see everything works the way we anticipate. So the first thing I have to do is to say, at the moment, if I try and hit the run button, it's going to complain and say something's wrong. Okay, so there's stuff that's not defined. If I go and I click here, if you look here at the top, there's a map view, which is what I used. It's a simple view, and then I've got a model view. The model view shows me that I need information. First characteristics, let's start with our stock. The most important thing about a stock is a stock needs an initial value. I'm just going to trial this, so I'm going to start off with an initial value of 1,000. I know there's no population that's small, but let's just use that to see if we can make the model work. In terms of an equation for our birth rate, this is a simple one. It will say population of people multiplied by our birth rate. So that's an easy one. And then birth rate. This is a more difficult one. And I said earlier, you need to know your domain. One of the things that I've learned through the years is the more time you spend discussing and asking people in a specific domain about their domain, the better you understand what they're planning to do, and the better you understand the numbers that you need to put in here. So I know quite well that what numbers don't work and what numbers do work. So let's try, just for simplicity's sake, I'm going to say that there's a 2% birth rate. This was actually the South African birth rate in the 1990s, was just over 2%. So this is a valid number. If we look at the death side, and again, this is where you need to really fundamentally understand the domain you're trying to model in. If we were using a death rate, we would use exactly the same kind of equation and say population multiplied by our death rate. Because I'm using life expectancy, I have to think a bit more clever. And the technique we use there is to say population of people divide by life expectancy. And the effective result that you get here is an F distribution. And what an F distribution does, it says on average, people will die at the time of my life expectancy the most, but there will be a tail that says some people will be older and some people will die younger. So that gives me a much more realistic perspective on the population that I'm trying to model. You know, we don't have Logan's Run where you get exterminated at the ripe old age of 40, which is a great idea given that I'm not that young anymore. So let's just, and I'm just going to again just use a simple number. I'm going to put in a number of 60 here. So it says 60 years. But I'm going to do another cheat now before we start running this model. Sorry, let me just first get us a graph so that we can track our population on it. So we can track our population. But the first thing I want to do is I actually want to multiply this equation by 0. Okay, reason why, if I put a life expectancy of 0, I'll have a divide by 0 and this thing won't work. But what I'm doing now is I'm demonstrating what happens if I have an exponential growth, because I expect my population with a fixed birth rate to give me an exponential growth. So let's see if that is what happens. And lo and behold, yes, we get exponential growth.
Sorry, Gift, did you have your hand up?
Yes, I had my hand up. Dr. Botha,
Yes, sir.
On the birth side, we have the flow, the birth rate as a converter, and then we have birth there as a flow. Shouldn't the birth rate be associated with the flow instead of the converter?
The birth rate is the converter. So the birth rate is linked. So there's a link from the birth rate to the birth to the flow. So there's a flow that's linked into the population, and then there's a feedback loop that says the number, because you have to have people. I mean, one of the silly things one sometimes does is you initialize by 0, and you then run the model and nothing happens. So you can see here the two links. So there's a link from population to births, which basically says it brings the math together that says population times birth rate gives you the births. Okay. So you can see the link. Sorry, they don't make them very, let me just see if I can make them a bit thicker. There we go. There you can see them now. Okay, so you can see the two links. So there's a link from the converter to the flow, and there's a link from the stock to the flow. Okay, so at the moment, I've got a zero population, so that's not a good idea. So what I'm going to do here is I'm going to put in 100,000 people. I'm going to put in a birth rate of 0. And I'm going to unblock this life expectancy curve of us. So let's see what happens if we run it to this side. And there you can see that you start off with your population. Some of them die relatively quickly, but over time there's some people who actually last the full 200 years. So my expectation of growing to 200 years is cool. I'm sorted there. But basically what I've done now is to just confirm my logic. Does my logic make sense? And let me just go back. I think I've got a bit more in the presentation for the next bit. Okay. Oh, yes. So the next step. So we've now basically done what I would call a validation. So we've checked, does the bits and pieces operate the way we want them to do? So what I want to do next is to say, okay, let's calibrate this model. Let's put some real data in and see how the model behaves under those conditions. So I'm going to go back to the model. Going to go back to my model, and what I want to do now is to put in real numbers. So we've got two options. I can put in the South African numbers, or I think more importantly, let's put in the global population. So we've got a global population of 7.71 billion. I think that's enough zeros. Okay, so I've got 7 billion people. I've got a birth rate of 1.07, and I've got a global life expectancy of 72 years. And what do we expect to see from this population? I'm actually not sure. This is interesting. This suggests that at the current birth rate, that we should see a decline in population over the long term, and that we've already reached our peak. Let me try another round. Let's try and put in here the South African population, which is 59.3 million. We've got a birth rate that's sitting at 1.34%. And we've got a life expectancy that is not 72, but 65 years. And we run our simulation. And we're also seeing that our population is dying too fast. Hang on, something not lekker. Got that right. Oh, sorry, it's 1.34%. Sorry. There we go. You see what happens sometimes is, ooh, okay, now we've got exponential growth. It goes crazy. Let's try the world population again. Actually, let's just try the world population indexes here. 0.7. And we still see that. So definitely, my original number that says divide by 100 is correct. So this is part of that exercise where basically when you try and calibrate, you really need to be very, very cognizant of your numbers. I know the closer to correct number, as I said earlier, in South Africa is 2%. So let's just see what 2% does to the population. And there we see an increase in the population. And this is where the system dynamics tools become really useful, because now I've got a model where I've gone through a bunch of assumptions. I've confirmed my assumptions, and I've confirmed that the model is behaving the way I expect it to do. But, you know, so what? What do we do to make this a lot more fun? So answers the question what to do. And this is where scenario analysis comes in, where we basically want to define what scenarios we want to test, We want to define how to set up that scenario, and then we can have some fun and make things happen. So I want to go back to our model, and I want to show you what is, and I'm just going to do some quick analysis, so don't expect the whole lot. If you want to see the whole lot, please attend our or join our modeling competition. During that, I go through this in a lot more detail. But for example, one of the things that we've put in here is a fixed birth rate. The reality is that birth rate is not really fixed. Birth rate is something that changes over time. So how do we enable that within a model like this? So what I'm going to do is I'm going to make my variable here time, and then I'm going to create a graph, a graphical function that will allow me to put different alternatives in here. And I can say, okay, well, I know my birth rate started at, and I just need to do another little cheat here quickly. I'm going to work in percentages, so I'll divide this by 100. Sorry?
We just have a comment for you. Cello says, how about if you include migration and immigration?
Now we come to the question of what is the domain and the purpose of the model. I am just trying to demonstrate what we can do with this. Am I trying to build a real life model? No. If I'm trying to build a model of South Africa and a population model of South Africa, and I do not include immigration and immigration, legal, illegal, the whole story, then the model will be insufficient. So if I just use this model and say, plan your schools, plan your infrastructure based on this model, the answer is wrong. And there's no point to use that. So that's why it is so important to understand the domain you're working in, but also what is the question you're trying to answer. If you're just trying to get a rough estimate of the number of people, this is adequate. If you're trying to plan your hospitals, your infrastructure, as I said, even building a model with immigration and immigration of South Africa as a whole would be a simplification, because you really need to look at urban, rural, that whole urbanization, and how do people move from the urban areas into rural. Some older people retire in the rural areas, but then you've got the youth that are moving into the cities to find work. So there's a lot of complexity that you can build into a population model like this. I can't do this tonight. I mean, there's just not enough time for us to do that. So what I'm planning to do is to just give you a quick glimpse of some of the work that can be done. So for example, if I start here and say my birth rate, oops, it's going to start too low. I just want to get that first one. Okay, so if I want to create a curve, and let me just go to the graph quickly, and I want to turn this, let me just do this. I just restore devices. Sorry, I'm working in the dark here. Eskom is helping me learn how to model in the dark. So if I run my simulation now, I can see what, for example, is the impact of the birth rate decreasing over time. So whether it be education, whether it be affluency, whatever the factors might be that influences birth rate, we can now start seeing what implications it has to the population. If at the same time I say, but hang on, people are not dying at 65. What we are seeing is that we're also seeing that people are growing older over time. So what I'm going to do here is to include a graph here that starts at 60 and says our life expectancy here at the start is 60, but over time we expect that to increase for, again, whatever reason, whether it's better nutrition, whether it's a breakthrough in medical technology. That is not important. We can expect our birth rate to increase. And now suddenly we can start seeing what the curve does. And it's not about getting a perfect forecast. The reality is there's no simulation that will give you a perfect forecast of something like the population. However, we can start building understanding of what is the big drivers and what are the implications of going in a certain direction. For example, one of the elements I haven't even brought in here is to include a stochastic component. So let's try something like that. I'm going to leave that there. I'm going to just say that our birth rate is actually a it's a normal distribution.
Sorry, Andres, we have
running out of time.
No. We have one more comment here.
Yes, ma'am.
Sunita asks, she would like to understand something. In case you want to develop a model without available figures, for example, you are using population and we know that's estimated at 7 billion. What if you don't have an initial figure? How then do I develop a model and simulate?
I can tell you faith, hope, and love. The reality is, you know, what we need to do is to make logical assumptions sometimes. I know in this case, for example, when I'm looking for birth rate, I know there's quite good numbers out there. You just need to know where to hunt for them. And again, when you work with domain specialists, they tend to have numbers. If you're not sure, start with an index. You know, when I started playing with this, I used an index of 1,000. When I wanted to look at the deaths, I said, well, 1,000 will decline too quickly. Let's try 100,000. What you can then do is use a standard number and make sure that your numbers are relatively correct towards that number. So, for example, if I don't know what the South African population initial value is, and we don't, I mean, we guess, we can also, you know, do what I'm doing now with adding a stochastic component where we can have 50 different runs and have 50 different populations, like a Monte Carlo type simulation. We can set that up. That's not a problem. But I think the key is that the number needs to make logical sense. You know, so for me, a number of 59.3 million, that I got that off Wolfram Alpha. It's a decent number because I know that's about what Stats South Africa guesstimates at. It's actually, I think this is a Stats South Africa number. But yes, it's one of those components that I think tends to be, it is an art, but it's an art that's driven by logic. So you sit down and you work out. I think somebody earlier asked you, Nalini, how do you go about explaining a model of that complexity that you've got to an audience? My approach is to build the model on a whiteboard. So I stand with that audience and talk them through the logic of the model. Once you get the logic, then you can get the order of magnitude numbers, and that is sufficient. So in my opinion, data is a second order problem when you're doing a simulation. The key is to understand the domain, and then you can start bringing in those parameters and those initial estimates. And, you know, I can't emphasize this enough. All models are wrong. Some models are more wrong than others. Some models are useful. So if you've got a model that is, if you start calibrating against real numbers, you're looking between 80 to 90% correlation, then I feel that you've got a sufficient model for, again, for the purpose. If you want to do an accurate forecast or accurate prediction, then buy a crystal ball. Your number will be perfect every time. If you want a reasonable estimate, you use a simulation that's within 80 to 90% correct, and you don't give people one line as an answer. You basically do the following. You run the simulation a few times, and I usually let it run for 50 times. And then what happens is I start seeing a pattern emerging, and I can give you a confidence interval of my result. This one is, I mean, this is pretty simple. Let's say my estimation of the birth rate is really bad. Birth rate is really bad. And that variance is closer to 30%. We can see what happens when we run the simulation now. Now we start seeing some deviations that's much broader. Now, if you've got a reasonable number there and you run it for a reasonable number, you can calculate an average and you can put a confidence interval on that number given that set of runs that you've done. But there's no correct answer that you'll get it perfect every time. Okay, we are running quite short of time, so let me quickly just do the last few slides. Last slide, I think, last slide. Whoopsie. Sorry, there we go. The question I sometimes ask myself is, what can all the functions do? So I'm going to quickly show you my function tester, and then we can do a bit of experimentation with that. So I'll also build it down here. Basically what the function tester is I want a stock that says accumulated. I want a stock that accumulates. I want a stock that gives me sort of the instantaneous effect.
We are seeing you, but we are not seeing the model.
Are you not seeing the model? Sorry, I'm throwing the model big time here. Let me get the model going. There. You see the model now?
Yes.
Okay, cool. So I've got two stocks, a thing called accumulated, a thing called instantaneous effect. Got two flows, flow in, and I'll have a second flow. I'm not going to name them that, you know, just, and again, there's my check. My stocks are connected. So this accumulation is very simple. I will always keep this as a reservoir. So it basically says everything that goes in there will stay in there. If I look at my instantaneous effect, I'm looking for a time delay that will allow me to see what is happening. So the way I do that is I create a conveyor. And what I'll do with this conveyor is I'll give it a transit time of 10 time units. I'm going to have to change my runtime. I'm just going to do this quickly and do 0 to 20. Okay, I'm going to say my initial value here is 0. And what I can do now is I can do the more visible one to say, this is my equation controller. And then this will just be connected to that. So it's a one-on-one link. You can actually do the equations in there, but then it's not visible what I'm trying to do. So for example, let's get a graph here quickly. On the graph, I want to, sorry, is there a question? Oops.
I think that there's some in the chat, which I think Corne's been able to answer. So
thank you, Corne. Okay, so what I'm going to do now is to just check my accumulated, my instantaneous flow, and I want to check flow 1. Okay, so if I, for example, say, I'm just going to use a simple equations to say if time equals, oh, sorry, I can't see my keyboard, equals 5, then 10, else 0. So what do we expect? We expect to see a value of 10 going through the flow. It should go through the instantaneous effect, and it must go into the accumulator. Okay, can we quickly have a poll? Who says yes, who says no? I'm saying no. Look at this answer. It actually does not get to that value, because what is happening here is I am putting in an instantaneous number. That instantaneous number is 10. In the flow, it gets multiplied by dt, which is in this case 0.25 or 1/4. So the net effect is, while this pulse or this flow is equal to 10, the value there, the actual number that flows into my instantaneous effect is just 0.25, or 2.5, because it's 10 times 0.25. And then my accumulated stays constant. So let's see what happens if we do this and we say if it is greater or equal. I expect that increase now. And there you can see how it goes up until I've accumulated my full amount in my instantaneous. Because remember, it's been fed now. Why is instantaneous going to this big number and not sticking to the little number I was looking at? This is very simple because remember, it's adding up 10 time periods worth of stocks here. So it's basically saying that 5 that I'm putting in, or the 10 that I'm putting in every quarter, or every 0.25 time intervals, is just adding all of them up until it does hit 100, which we expect. But what you can see again, our accumulator is lagging behind. How do I go about getting a specific number of 10 into the system? So what I'm going to do is just show you a few quick tricks. So if time is 5 and I put in 10 divided by dt, you're going to see what happens to my spike. My spike goes up to 40. But my instantaneous effect now goes up to 10, and then it goes to the accumulated, where it basically will then stay with that 10. There's an alternative way of doing that. I can also do this with a pulse function.
Sorry, Andres, if you can perhaps conclude, because I see.
Yes, I am. This is now my last one. So all I'm saying is, guys, if you want to, this is a nice little tool. Put it together, and it allows you to test any of the functions, whether it's a complex function, whether it's if you want to see if the random number generator is really random. That is actually quite a useful tool to do that. And the answer is no, it's not really random. So what we'll do is, again, if anybody is interested, you can contact me and we can discuss this little tool. I think it's a useful thing for just knowing what's happening in the software. And that basically concludes what I wanted to say. So I don't know if there's any questions. I apologize for us running a bit over time, but please, any feedback after the seminar as well. So if there's anything that you want us to change, anything you want us to add, any topic you want us to try and get onto the program, please send us that information and we will see how we can accommodate. So thank you very much.
Thank you so much, Dr. Botha. I think this marks the end of our seminar. I don't know, Dr. Nalini, is there anything else that we need to say?
No, there isn't. I think we can stay on for another 10-15 minutes if anybody wants to hang around just to have a chat about certain questions that they have or any queries. So I'm prepared to just stay on for another 15 minutes if people want to ask anything else.
Yeah, I think I see you've also already answered some of the questions. In terms of modeling, the reality is you can make the model as complex as you want to. You can put as many flows, as many stocks in a sequence of flows. Some of the stuff I play with is chemical reactions, where we look at the control systems, where there's multi-steps in the process. These business processes. So the level of complexity is not limited. What is limited is your ability to make the model work. So my first rule of thumb, well, actually my only rule for modeling is simplify, simplify, simplify. If you can make the first stock work the way you want to, and you add the second stock and it works the way you want to, and you add, by the time you get to the fifth set or the fifth stock or the fifth train of stocks, if things then start going out of or become unexpected behavior, then you can start interrogating that specifically because you know that your model works. And I find that is sometimes where people get lost in modeling, where they build the whole model and then try and populate it with data and try and make it work. I tend to build component 1, test it with some arbitrary data, or stick some real numbers in, and then go on to component 2 and component 3 and element 4 and element 5. Because otherwise, I promise you, I can show you how to build a complicated model in 30 minutes. It takes me a day to train you to do that, but you can build a complicated model in 30 minutes. It will never run. I'm very good. I can build those in 20 minutes and they will never run. The reality is, if I build a simple model that does run, I can guarantee you that the integrity of that model will stay sound with every level of complexity that I add.
So before we continue, as we're losing more people in this seminar, I just want to thank everyone before they disappear for actually being part of our seminar. And we've sent a whole lot of links on the chat for the competition that we host every year via Carne and Andres. Then for the conference that we're hosting, which is also free this year, so there's lots of free stuff from the chapter. And part of the competition, just by the way, there's a whole series of workshops that are all free if you do register to take part in the competition. For the conference, as mentioned in the beginning, there's various options for registration and submissions. And then there's the student registration links, which I've shared. Remember, for students, even though it does ask you to send proof of payment, you have free entry into all of the events and activities organized by the chapter up until the end of June. As a non-student, you unfortunately have to pay, but it's really a small amount in the bigger scheme of things. That amount, we generally just use that for our accounting fees and just generally trying to keep the chapter afloat and running things, operations. So it's a small amount. So that's it from my side. I would also like to thank Dr. Young and Phyllis for hosting our first seminar. And I really do hope to see everybody in the next seminar as well. Like I mentioned earlier, we will stay on for a few more minutes. If there's any questions or engagements, we can take those. If anybody has anything, you can just raise your hand. Gift, can we see you on video and then have you engage with us?
Yes, thank you, Dr. Nalini and Dr. Botha for the great lecture. My question relates to the model that we've seen, and I know that he did not talk about the causal loop diagrams. But what I wanted to find out was that, as you develop the causal loop diagram, you are able to identify, all the necessary variables that would also be required when you develop the stock and flow diagram. So the question is, with regards to some of the converters and, that you would require in your simulation model, is it possible to read that off the causal loop diagram, or is it something that has to be, developed, as you go through the simulation model?
Give that is a brilliant question. The practical experience I've got says that I'll go and do interviews. So, for example, I need to understand the company's business. So I'll go and do interviews. I'll sit down with every person involved, right from the executives to the lowest level, map it out, put together a causal loop diagram, take them through it, confirm that everybody is happy and we understand. and then I start building and I start calibrating, and suddenly the result makes no sense relative to their real performance. I had a very particular case where the performance improved, but my simulation said the performance stayed static. So I